So, as we now continue with the PNA 2.1, one other aspect which we should notice here is that the origin now, see everywhere hereafter the definition of the location of the origin is important. Once we draw these two diagrams refer to some origin 0 0 0, and in case there is a center of symmetry, no problem, because the 0 0 0 will coincide with the center of symmetry. But in case we do not have a center of symmetry, we have to specify where the origin is. So, in this particular case it is at 1 1 2 1. So, the 2 1 screw axis in the z direction is now coinciding with the origin. So, that means the value of z is put equal to 0 at that point. So, this is very crucial because we have to define the origin term very clearly. Now, we go to the next system in the orthorhombic symmetry, which is all three mirrors. So, you see that the diagrams start to look more and more complicated, but once you have got the gist of it and you have understood what is it all about, it becomes fairly straightforward. Let us see how quickly and how comfortably we understand the space group PBCA. This is another space group which is fairly common among various organic and inorganic compounds, particularly when you have a flexible inorganic system or organic inorganic framework structure and so on. PBCA is a preferred space group. Now, therefore, we should know something about this space group. You see that space group number is 61, you are graduating very fast towards 230. In fact, after this I do not think we will do any more. So, we can as well say we are now coming towards the end of understanding the space groups by looking at two diagrams and then comparing those two diagrams with the equivalent points which are appearing in the next part, next page in fact in the international table, and next slide in our presentation. So, let us see what happens in case we have a PBCA. See, one of the things which is immediately obvious is that it is a primitive lattice. So, we will not have any centering information coming in, any phase centered information coming in and things like that. So, this therefore is a situation where we have no problems, primitive, and there is therefore the number of lattice points will be 1. So, we have to worry about only one lattice point. The moment we bring in a C centered lattice, let us say it is CMMA or something, or CMNA or something, in which case we have to now bring in two lattice points, one at xyz, the other at half plus x half plus yz. If it is a face centered lattice, we have to bring in 4 lattice points. If it is a body centered lattice, we bring in 2 lattice points. And I am bringing that discussion here because orthorhombic symmetry allows for all kinds of lattices. It allows for the primitive lattice, it allows for A centering, B centering, C centering. Of course, A, B, C are interchangeable. So, we can always say it is A centered or C centered. Once we say that, they are interchangeable with respect to each other because the 3 angles are 90 degrees with respect to each other. A not equal to B not equal to C. So, but we can define ABC as BCA and CAB. So, the symmetry is still maintained. The 360 degree rotation of the symmetry is still maintained, and so we can call them interchangeably. The interesting fact is that since all these possible lattice symmetries can come up in an orthorhombic system, it is very easy to interpret it at this stage. So, whenever you have a primitive lattice, you have only one lattice point to worry about, x, y, z, and whatever symmetry elements we generate is purely by symmetry operations. If you have a F centered lattice, there are 4 center related operations, the face centered related operations. So, for an every x, y, z, you will get a half plus x, half plus y, z, half plus y, half plus z, x, and so on. So, 4 of them you will get. And if it is a body centered system, you will get for every x, y, z, half plus x, half plus y, half plus z. So, whatever symmetry operations you are now going to perform on x, y, z, the same symmetry operations you have to perform on the next lattice also. So what happens is that the number of equivalent points will increase, but the number of symmetry related points will still remain the same. So in other words, if this is instead of PBCA it becomes IBCA, what will happen is that the number of equivalent points which occur here, which is in fact 8, will become 16. So the same 8 will exist with the same symmetry, but now all of them are moved by half along the unit cell. So additional apparitions of symmetry appear, and the signature of the point group symmetry remains exactly the same. So whether it is PBCA or IBCA, the point group symmetry is still MMM, and this is a point which should be noted, and this is a point which is going to be important when we actually try to solve the structures and fix the positions of the atoms and so on. So the lattice points will see all the symmetry operations associated with them independently. So if it is a C-centered lattice, we will have 2, I-centered lattice 2, and F-centered lattice 4. I am a bit repetitive, basically to drive home the point that you have to worry about these issues when you derive the equivalent points, and particularly when you try to discern the difference between these two diagrams which are shown here. So this diagram shows you the symmetry points, and this diagram now shows you the equivalent points. So the space group number is 61, and you see the full symbol. The full symbol is 21 by B, 21 by C, and 21 by A. Obviously, because we cannot have an MMM combination. We have already proved long ago in the earlier classes that a improper combination is not allowed. So it has to be when we write MMM. That is why we are happy to write MMM, because MMM actually represents 2 by M, 2 by M, 2 by M. And therefore, if you now see the independent derivation for each of these in the full symbol, you will see it is P 2 by M, 2 by M, 2 by M. In fact, that is what it is, and we reduce it to PBCA. So when we say PBCA, the 2 and the presence of 2 1 with respect to each of the axes is already implied. It is already there. So in the way in which we describe this space group is that we have a primitive space group. There is a B glide perpendicular to a C glide perpendicular to B, and A glide perpendicular to C. Suppose I have a space group which is PCAB. Is that possible? Is the question. So this is a question which we can answer right away. Suppose instead of PBCA, I have a space group. Let me write it down for you so that we discuss that. Instead of PBCA, we have a space group P C A and B. PCAB. Is it a possible space group? If PCAB is a possible space group, is it different from PBCA, or it is a new space group? We said there are only 230 point space groups, right? And is it going to define a new space group? These questions come up. So a primitive lattice is a primitive lattice, there is no change. What it represents here is there is a B glide perpendicular to the A direction. Here there is a C glide perpendicular to the A direction. And in this case there is a C glide perpendicular to the B direction. Here there is an A glide perpendicular to the B direction. And in the last there is an A glide perpendicular to the C direction. There is a B glide perpendicular to the C direction. So what is the answer? The answer is inherent in this definition, the way in which we now invoke the presence of the glide planes. So PBCA is a commonly represented space group which refers to A, B and C axis. Now what all you have done is you have taken the C axis to be B, okay, and the A axis to be C, and of course the C axis to be A. Okay. So since you have changed the axis directions, the glide plane directions have also changed. Remember, in an orthorhombic system, the 3 angles are 90 degrees with respect to each other. A is not equal to B, not equal to C. So we can call any one of them as A, any one of them as B, and any one of them as C. So, we can have therefore equivalences of space groups. So, PBCA is same as PCAB, except that your ABC positions are interchanged. So, in this particular case the positions are ABC, okay, and in this particular case the positions are, this position with respect to this is A and this is B and this is C. Am I right? C perpendicular to B, A perpendicular to C. Yeah. So, this is your crystal system now. It does not matter whether B is C, C is A or A is B, because we can interchange them with respect to ABC. So, these two space groups PBCA and PCAB are one and the same. So, this is something which we should remember when we are dealing with the orthorhombic systems. In orthorhombic systems we can therefore, it may so happen that your molecules, they do not know the definition which you want to give. They do not know which should be A, which should be B, which should be C. Your molecules will go and crystallize, and when you go to the machine and determine the space group, believe it or not, the computer says it is PCAB. Then you will quickly go into your international tables, PCAB, PCAB, where is it, where is it? You want to see where the equivalent positions are, and you will never find it. You will never find it because the standard for this is PBCA. The standard space group, as we call it, or the normally accepted space group, is PBCA. So, that means you have to change your axis directions. Your ABC now has to follow the PBCA point, the space group. So, the ABC should be changed such that we get a B axis perpendicular to a C axis perpendicular to B, and an A axis perpendicular to C. So, when we do this particular change, then it is one and the same. So, this is something which you should remember, and then whenever you have a situation like this where the molecule has gone into PCAB, you can either change the symmetry elements and make them into PBCA, or you solve the structure in PCAB, but eventually report in PBCA. All are allowed. It depends upon what you would like to look in that molecule. Suppose that molecule has a very special behavior. Suppose there is one direction which is very, very large, and that is the direction which is very crucial for the property that compound is showing, and that happens to tell us that the space group is PCAB and that large direction is B. Then we would rather keep it in this form than report as PBCA. So, you will see lot of literature, particularly in inorganic compounds and also in materials oriented compounds. The space groups which are not the normal space groups are acceptable. But what people do is, when you read that literature, in the brackets they will give the standard setting is PBCA. So, they will indicate that even though the structure is reported in this space group, the standard setting is PBCA. So, this is how the space groups are unique, and therefore, there are not more than 230 space groups. Otherwise, the numbers would have increased enormously. For any given A, B, C, we can define these interchangeably to the combinations. So, the combinations will keep on increasing, which we do not want to consider. So, PBCA is number 61, and if you crystallize the compound and it tells you, the machine tells you when you do the analysis, it is PBCA, you do not have to panic, it is still the space group 61. Either you convert all these things to PBCA, which would be the most safe thing to do, but if you do not have to do it, because you have something very special in your compound which is along the B direction, and that wants to be along the Z axis, keep it along the Z axis. Suppose you have a crystal grown in that direction and you want to measure some property associated with the crystal. Of course, if you have a PBCA crystal, it may not be very interesting because it is nicely beautifully center symmetric. But if you have a system where the non-centric behavior comes up, PNA, the previous space group which we discussed, for example, PNA 21. So, suppose you have an N glide perpendicular to A axis, A glide perpendicular to B axis, 21 is along the Z axis. You may have a equivalent space group P21 NB. So, this P21 NB is equivalent of PNA 21 for all practical purposes, because we can change A, B and C. So, this particular table where we can have the standard representation given in the international table and all other possible variations which come up due to A, B and C being interchanged, A table of that is provided in the international tables towards the end. So, we can go to the end of the international tables, look for these tables in case you get a space group which is not listed in the 230 space groups. The computer will give you the space group whatever it finds with respect to the molecular system which is there in your crystal, because it is going to base it on the diffraction conditions which it finds. And once it has happened, then one has to go and look at the standard setting. And so, when you report in literature, you have to report the space group in which you determine the structure. Within bracket you should say standard setting is PNA21. So, it may be very important that this 2-1 axis which is found in PNA21 has a very special property like ferroelectricity or ferromagnetism shown in that particular direction, and you want that to be z axis because your crystal is grown in that particular direction. It is very clearly seen in the morphology of the crystal. Then we would rather maintain that particular space group rather than report the standard space group. So, this is something which you should bear in mind and never get into troubles when you discuss this. So, when we go to PBCA, therefore, these are the equivalent point positions. I want you to do a little exercise again here. The exercise is to compare these and see which are these corresponding. This of course is very straightforward. Here you have a center of symmetry, and this to this is now you are all experts. So, this to this is now the glide plane and also the 2-1 screw. You see that the 2-1 screw and the glide plane coincide because you have a system where this is the A direction, and in the A direction you have a B glide which is perpendicular to the A direction. You also have the 2-1 axis in that direction. So, the 2-1 and the glide, they move by 1/4. So, this is the glide direction, and similarly the C axis and the Z axis, the B axis and the C axis are also having the glide planes with a 2-1 screw which is now removed by 1/4 here, and in this case again it is in plane. So, you notice that whenever you have a glide and the associated 2-1, they are in the plane of the diagram, whereas whenever you have the center of symmetry and the 2-1, the 2-1 symmetry goes by 1/4. That defines the translational periodicity, which is half unit along A, half unit along B, half unit along C. And therefore, you can now correlate this diagram with this diagram, and at the same time also look at the equivalent points. And here there are 6 equivalent points. Here is some thing which we have to see. 1 and 5 are shown as x, y, z, x bar, y bar, z bar. I want you to do a little exercise here. So, 1, 5, 2, 6, you take these 4 to start with and then generate these 4, and 1 is x, y, z. So, we go back to the previous slide. You see this is 1, okay, and then 5 is this one because 5 is the x bar, y bar, z bar. So, like that I want you to mark 1, 2, 3, 4, 5, 6, 7, 8, the 8 equivalent points in this diagram. And in this diagram we already know there are 8 equivalent points because z is equal to 8. So, I want you to isolate and identify the equivalent points which we have in the next slide with respect to 1, 2, 3, 4, 5, 6, 7, 8, whichever is there inside the unit cell. I want to also tell you that it is still only 1 in the asymmetric unit, and I want you to verify doubly why it is still only 1 object inside the asymmetric unit. You notice that the asymmetric unit has shrunk now. It is x half, y half, z half, and you see all other generations which you are making is either half plus or half minus. So, that does not go with the existing one. So, you will have therefore only 1. So, the primitive lattice is dominating in this particular structure, and that is how it is a primitive lattice. If it is centered, you will have 2, and if centered 4, and so on. Right. So, the other thing which you have to notice here is that this also has special positions, and these special positions, both of them are center symmetry. Now, this is something which I want to discuss a little bit here before we end this particular session. The discussion is the following. See, when we look at, you see this is the C2 by C system, right? C centered lattice, a 2 by C as the point group which gives rise to 2 by M in fact. And you have these diagrams, and you have related these 2 diagrams beforehand. Now what you do is you look at the special positions. Here there is special positions associated with 1 bar as well as the 2-fold. The space group has the 2-fold and the 1 bar. The space group has also got the C glide, but there is no possible association with C glide because it has a translation component. Agreed? Now, whenever you have a translation component symmetry element with a space group, that particular component will not have special positions with respect to that. So, let us go now straight away to the space group we have been discussing, because that is where a very important point comes up. If you see here the PBCA space group, what is your take home? You have 2 1, you have B, you have 2 1, you have C, you have 2 1, you have A. So, what would be the special positions? The special positions cannot be associated with any of these symmetry elements individually. So, there cannot be anything associated with 2 1, there cannot be anything associated with B, it cannot be anything associated with C and A. So, what is it? Where is this special position coming in a space group like this? If one examines that carefully, you have a solution to the problem. In this particular case, you know that this is a center of symmetric space group. Center of symmetry is not associated with any axis or any translational periodicity. The periodicity that comes up from a center of symmetry is only one unit along x, y or z. And then of course, it appears also at the half position as a consequence of symmetry. In other words, this 2 1 position can be this center of symmetry position can be also this center of symmetry position or this center of symmetry position. That means, this framework is the lattice, and this lattice we can slide down in all 3 directions, and again we have the position of the center of symmetry fixed. And since the center of symmetry is a fixed position, we will have special positions when the atom or molecule or the system which we are discussing sits at the center of symmetric position. Okay, it is very clear, very simple, and therefore, you see now the special positions will be associated only with 1 bar. You have all the other symmetries, but only 1 bar is allowed. So, if you look at all the special positions which you come across in the 230 space groups, all those special positions will occur only with symmetry elements which are not having translation components. So, it will be 1 bar, it will be 2, it will be mirror and things like that. Okay. It will not be associated with any of those. So, 1 bar, 2 and M, these are all the special positions you will have. Of course, you can have combinations of those. For example, in a 4-fold symmetry, you may have a 4 by M symmetry. The 4 by M symmetry in principle is center symmetric. Even though you have a 4-fold rotation, 90-degree rotation coming up, it is in principle. So, it could be offering a special position. So, when one studies the international tables fully, which we are not going to hereafter, we are going now a little forward and go eventually to the structure determination protocols and so on. At this particular position, what we have to therefore do is to consolidate what we have learned in space groups. And to consolidate what we have learned in space groups, the best example would be to take something which is a realistic structure. Look at a realistic structure and see how the realistic structure distributes itself in a given space group. I have purposely taken a space group which is not a standard space group. The corresponding standard space group will be what in this case? PMCN, find out. A mirror perpendicular to a C glide perpendicular to B, and N glide perpendicular to C. So, we will have to find out what is the corresponding standard space group. So, we have to go to the international tables and go to the end of the international tables, look at what is appearing as PMCN, what is the translational change we have to do, because it is an orthorhombic system. So, A, B and C have to be interchanged. What interchange will give us the standard crystal system? That is first thing we will do in the next class. So, to wind up this particular class, we will see that we have the space groups now identified up to orthorhombic symmetry. We have seen the triclinic system, we have seen the monoclinic system, we have seen orthorhombic systems. In orthorhombic systems, we have seen all possible point group symmetries. We have seen 2, 2, 2, we have seen MM2 and MMM. Now, in that we have considered all possible variations. We have considered the possibility of introducing 2 1 axis, and we have introduced the 3 non-intersecting 2-1 axis. We have also introduced the positions, 2 mirror positions and 2-1 axis, the 2 mirrors now having glide planes like PNA 2-1, which we have seen. And we have also seen PBCA, which will involve the 2-1 by M, 2-1 by M, 2-1 by M centrosymmetric operation. We have examined in all cases wherever a special position is possible and in what way the symmetry elements rearrange themselves in those special positions, starting from the triclinic system. We started from P1 bar and ended up with this particular thing. So, in essence, we have covered now all aspects that are required to be known in space groups. We have not gone to the higher space groups because of the fact that it is not required for this course, because now here onwards we have to find out the methodologies by means of which we find, given a crystal, how do we find the space groups and how we assign the space group to a given material, and then how the material arranges itself in 3-dimensional space. So, we have come to that level, and therefore, what I will do is I will take this system PMCN and in this take an example of a known compound, and we are going to look at the known compound being calcium carbonate. So, in the next discussion we will look at calcium carbonate and see how calcium carbonate, the calcium, the carbon and the oxygen atoms arrange themselves in this space group PMCN, keeping all the symmetry information intact, how calcium, carbon and oxygen decide to go into this unit cell. Now, how will they go into the unit cell is a very open question. So, we will have to therefore in principle find out how many such calcium carbonate units can go into this unit cell. So, how will we do that? We do it by determining the unit cell dimensions. So, we know the ABC values. If we know the ABC values, we can calculate the volume of the unit cell. Having calculated the volume of the unit cell, since calcium carbonate we know the molecular weight, we can now calculate, given the volume and the molecular weight, the density of the crystal, assuming that this particular space group has so many equivalent points. So, PMCN we examine with respect to equivalent points, and these equivalent points, how can we distribute the density which we can have in this particular case for calcium carbonate. It is also suggested, and in fact in our school days, I mean when we were studying for our PhD, not school days, whenever we looked at a crystal structure and whenever we grew a crystal, we were asked to determine the density of the crystal. In fact, papers were not getting accepted without the acceptance of the density of the crystal, and therefore determination of the density of the crystal is very important. How are we going to determine the density of the crystal? So, we will start the next class from understanding how we determine the density of a crystal, which is very crucial. And then we see once we have the density, we have the molecular weight, we have the volume from ABC values, we can then calculate how to distribute individual atoms inside this, keeping the symmetry in mind. Now, I am saying as though we have all solutions for all crystal structures. Obviously not, because we are taking a very simple compound, calcium carbonate. Suppose we have a very large molecule, suppose we have a protein, I cannot use this approach which I am going to describe to find out where these atoms are. This is a very simple structure, and it is going into a space group where it has to obey certain symmetries, and therefore, whatever symmetry it is going to obey, we will try to reconstruct the structure in this particular space group.